Hello, I'm Alfredo. This is the walkthrough for my Kaggle notebook that I developed with Filippo Loddo for Project 7, Transformers versus Convolutional Neural Networks for Medical Images Classifications. Okay, let's start. You can see I'm on Kaggle. It's useful because it's easier to import the dataset. In Kaggle, you don't have to download anything. So we start with importing the libraries. I suggest that you enable the accelerator, the GPUs. You need just a little bit, few lines of setup later. Here we we detect the device, which is CUDA with 2 GPUs. And now we load the dataset. So as you can see, the dataset is comprised of a few folders. We have the test, training, and validation folders with the images and the data frames in CSV format. So how does it work? We need to load the data frames and we need to extract the ground truth, which is what is the labels of all the images. We can see this for these images. For this image, we have one hot encoding. This is a class MV. We will see later what it means. So we load the dataset and we use this. We declare this class. First, I want to talk about this dataset. So I will just show you a few images taken from this dataset. As you can see, it is from skin lesions classifications. We have melanoma, melanocytic nevus, basal cell carcinoma, actinic keratosis, benign keratosis, dermatofibroma, and vascular lesions. We have 10,000 images in this dataset. And what we need to do is we need to accurately classify each of the image in the test set by training it with the models. The main objective is to evaluate if the transformers or the CNNs are better for this purpose. So we start by doing this dull razor artifact removal. What this does is it converts the image to grayscale with a structuring element, does the black hat morphological operation, and then with thresholding, we inpaint only the parts of the image that are detected as hair. This is done to remove the hair that can introduce noise. As you can see here, we have some hair that gets removed, and this can improve the performance of the model. We will see later if it really did or not. After, so here we see the transformation that we do on the data. We do resizing, then the dull razor, and then we do some random flipping, random rotation, color jitter, without saturation and hue, because we don't want to alter the original color, since it is relevant to the final diagnosis. And you can see that we need to also resize, the most important is to normalize the image. And we also need to resize and transform and normalize the evaluation, so the test set and the validation set. This is because the model only knows those kind of images. You cannot show the unnormalized, untransformed images. Okay, so we load the dataset. It's because I didn't. we load the dataset, and we show some samples, some random samples, just to see that everything is working. You see random rotations, random resize, the standard resizing and normalize, and no, it's not normalized because we need to unnormalize to visualize it, but it's transformed. So as you can see, the dataset is extremely skewed. So we definitely need to take to account for that later. Here we just check if all the split, see the split is uniform, and we can see that in every split we have kind of the same percentage of the 7 classes. So okay, here I showed you the 7 classes, and there is a brief descriptions. Okay, now we talk about the models. We have designed one CNN and one transformer. So the CNN has a custom head with 50% dropout. This is to force robustness, to have less overfitting in the model. And the transformer models just have some regularization to prevent also overfitting. To allow the accelerator to work, so to work on 2 GPUs, because we have 2 GPUs, you need to use data parallel so that you're able to split the work on the 2 GPUs. So you need these few lines of code. Here we define the class weights. This is very important. We can see here that what are the individual weight. So of course, for the most prevalent class, the weight is very low, and for the other classes, the weight is high. What does it mean? That the model will not just always predict the more prevalent class, and has to try and balance it with the others, so that we have a more honest evaluation of the model and it is not cheating. Here we try the square root smoothing because this is very extreme differences in weights. This is a bit smooth, but as we will see later, it didn't provide great results. Okay, so here is the training loop and the training pipeline. I will not be training because it's very long, but I have already loaded the best models, the models for all the different our different approaches. So now we go to the evaluation of the models. Here we load it from these folders and we evaluate it. We extract the accuracy, F1 score, outcrock, and recall. We use macro. Macro is better than weighted here because with weighted we will have more weight on the prevalent class, but here every class has the same importance. Ideally, actually, the most important class would be the melanoma and the more cancerous, more aggressive, but here we didn't account for that. Okay, so here we run the different models. We wait for the model to run. Okay, here we have the evaluations of the model. We have done a few trainings. So we trained the CNN without the dual razor preprocessing, then with the dual razor preprocessing, and then with the dampened weights with the square root. Also, we have trained the visual transformer with dual razor and without dual razor, and now we will see what the results are. So we have a few quite a bit of information here, but what are we looking at? So the accuracy is actually misleading here, as we saw earlier. we should not be focusing on accuracy, but rather F1 score or outcrock. It's also important to recall because in medical datasets, we really want to focus also on that. So between this nodal razor and the razor, we see that we have an increase in the F1 score, and that's good. Also in outcrock and in recall. So as we can see here, the razor with the dampened weights has a very high accuracy, but are very low, but it's lower in outcrock. That's very important, and in recall, and as the same, actually the same F1 score. This tells us that it's not the right path. Maybe some other type of dampening can help us, but not square root. So this is not this was not helpful. The VIT and with data razor we'll see later in more detail. Here I am plotting a confusion matrix that tells us where the models get confused between the different classes. And also, very important, the ROC curve. What does it tells us? This is the random guess, just guessing randomly the classes, and how much better the model is than the random guess. The perfect model is just square, but there is no such thing as a perfect model. We can see that the best classes that are very well recognized are like vascular, this is this, and also maybe BCC. Why is that? It's probably because they are the photos are of the lesions are very different between the others. So this allows the model to better separate them. Here is the curve for the VIT. Okay, so here we see the final comparison. As we can see, the best CNN is the CNN with the razor, so it helped with the CNN, but with the VIT it did not actually help. Why did this happen? This happened because in the inpainting process we are actually interpolating information between different pixels, and we are destroying some informations of the underlying image. So the VIT basically cannot understand, is not helped by this, but the CNN that is highly local actually has an advantage with this with the removal of the hair. We think also that the VIT is capable of isolating the features without the razor, so this is why it didn't actually help. So we can see that the accuracy is higher, the F1 macro is higher, the outcrock is higher, and the recall is higher. So this was not helpful. Here, this is the comparison on the plot of the comparison, and here are some final considerations that I already told you. The final cell is an error analysis. Just we want to see where did the model go wrong. Here, taking the target class melanoma. So as you can see here, we have the true positives. So the melanoma cases that were actually melanoma, and these the false negatives. So melanoma cases that were labeled as something else. So thank you for watching, and this is the notebook address I will link in the description, and goodbye.